Non-parametric test for correlation. If we suspect that the underlying populations are not normally distributed, in other words, they're not parametric, then we have to use what's called the Spearman rank correlation coefficient. So let's just stop there just for a quick second. In a previous module where we did a hypothesis test for correlation, the assumption was that the underlying populations were normally distributed. However, if we're told that the underlying populations are not normally distributed, then the test is done a little bit differently. And again, test for what? Like, what is it we're trying to achieve? We want to see if the correlation between these two populations, which in this case are not normally distributed, we want to see if the correlation between those populations is significant or not. In other words, is there a relationship between these two variables? So let's look at an illustration. Suppose we want to see if the correlation between hedge funds X and hedge fund Y are significant. Since we suspect that the returns are not normally distributed, we're going to use the Spearman rank. And that's kind of true with hedge funds, because with hedge funds they use a lot of leverage, they use option-like strategies, so therefore their returns are not typically normally distributed. So what are the steps when we're doing the Spearman rank? So first step is rank the returns of both funds, with the highest return being ranked number 1. So let's go ahead and look at here. Suppose we have 5 years worth of data. So in year 1, X had a return of 10, Y had a return of 12, and so forth. So those are the individual yearly observations. But the first step tells us is that we should rank these performances. So if we look at this 10%, let's just look at for X. And well, here, let's do it this way. Why don't we start with the highest? You could see in year 2, it had the highest rate of return. So therefore, this would be given a rank 1. On the other hand, you could see that -7 was the lowest return. And since there were 5 observations, this would be ranked number 5. And we do the same thing. We do the same thing for fund X. So here's a fund, we do the same thing for fund Y. Here's the highest return. So again, year 2 gets ranked number 1 for hedge fund Y. And the lowest return is right there. It happened in year 4. So therefore, this gets ranked 5 because this -2 of all the five years worth of data, this -2 was the last best performer. In other words, it was the worst performer. So there's your step 1, ladies and gentlemen. You just gotta take these annual rates of return and rank them. Let's see what step 2 is. Step 2 is calculate the difference between the ranks for each year. So here it is. So for year 1, the difference is +1. Right, and let's just pick year 3 just for illustration. 4 minus 3, that's also +1. And let's pick year 4. 2 minus 5 is -3. Let's just do all of them. Year 2, it's 1 minus 1 is 0. And then year 5, again, we're finding the difference between the ranks would be +1. So that's your step 2. And then finally, step 3, it says square the differences. All right, that's exactly what we do here. So 1 squared is 1, 0 squared is 0, 1 squared is 1. -3 squared is 9, and 1 squared is, of course, 1. Okay, and so the sum of the differences, when you add them up, it's going to be to 12. And so step 4, we actually find the Spearman correlation. And so this is the framework we're going to use, ladies and gentlemen. So it's one of those things where it's easier to commit to memory than to build this thing from the ground up. And this 6 is a constant. So it's got no relation with the number of years of observation in our illustration. It's always 6. So it's 6. Well, if you look at the whole thing, it's 1 minus 6 times the sum of the square of the differences divided by n times n squared minus 1. So let's plug in all these values. So there's a 1, there's a minus, there's a 6. And the sum of the square of the differences is right here. So here's the differences squared, and this is their sum. So that's where the 12 comes in. And then n is the number of observations. So in our case, it's 5 times 5 squared minus 1. So the whole thing works out to positive 0.40. So that's our Spearman correlation. In step 5, we find the t-stat. So this t-stat is very similar to the t-stat for population or for sample correlation that we found using the approach in a preceding module for correlation tests, except instead of using the correlation data from the sample, we're using this Spearman correlation. So let's go ahead and plug in all these values. So the Spearman correlation is right there, 0.4, and then n minus 2 is 5 minus 2, divided by the square root of 1 minus the r squared, which is right there. So the numerator and denominator works out to as follows. So therefore the t-stat is 0.76. And then finally in step 6, we do the hypothesis test. Now, when it comes to significance test, we always set the null equal to 0. And what we're hoping to do is we're hoping to disprove this. So if we disprove this, that means there is a correlation, right? But if we don't disprove this, in other words, we don't reject it, then it implies what it says right there. It says it's possible that the correlation between these two funds is 0. In other words, there is no relationship. So what's the rule of thumb? The rule of thumb is that if the t-stat, in other words, if the sample statistic is less than or equal to 2, in other words, it's less than 2 standard deviations away from the null, then we are 95% certain that the null is true. So here's what it's saying. Again, let me repeat this. Here's a null statement. Now you have to remember you're basing this test on a sample because you only picked 5 years worth of information. So what we have to do is we have to build in a margin of error around this null statement. And here's what it's saying. The rule of thumb is if the goalposts are 2 standard deviations away from the null, that's giving the null a 95% margin of error. So if the sample falls within, so here, let me do an illustration. So here's the null, and what we're saying is if you go plus or minus 2 standard deviations away, this covers 95% range for the null. So if the sample falls anywhere here, we go ahead and we accept the null. On the other hand, if the sample falls outside of positive 2 or negative 2, then we would reject the null. Now, in our case, in our illustration, you could see that the t-stat, which we calculated right here, was 0.76. And clearly, 0.76 is within plus or minus 2. So if I plugged in 0.76 right there, you could see it's within 2. And therefore, this is within null range. Therefore, we accept the null. And what does that mean? It means that based on our sample, we cannot reject this possibility, meaning that it's possible that there is no correlation between these two hedge funds.